thing before we get started today? So, we've been talking about how magnetic fields interact with charged particles. Additionally, charged particles can create magnetic fields under the right circumstances. The most common of those circumstances is by running electric current through a wire. The wire naturally creates its own small magnetic field. And because of the sort of right-hand rules nature of everything, where everything has to be perpendicular to everything else in this particular field, if, say, this is your wire and current is running through it that way, the right-hand rules tell us that the magnetic field is going to form perpendicular to that wire, but because field lines always have to go somewhere, it's going to sort of spiral around the wire within that perpendicular plane. So if your current occupies the X, Y, and Z axes. If your current is in the Y axis, the magnetic field is going to spiral in the ZX plane. And every wire with current running through it just creates this very small electric field about itself. And the way you can use right-hand rules to help predict this somewhat. Previously we were doing direction of, I guess it's a slight modification actually. If there's a current running through a wire, and you sort of grab hold of the wire with your right hand, if you point your thumb in the direction of the current, the magnetic field will spiral in the same way your fingers are curled.
Wait, what was spiral?
The magnetic field. It will spin about the wire, mirroring the direction and plane of your fingers curling. So in this particular case, current's going that way, grab the wire, wrap my hand around it. My fingers are currently spinning counterclockwise in the plane perpendicular to the current flow. And so the magnetic field will spiral counterclockwise in that perpendicular plane. This by itself isn't something that would be hugely problematic, except that most of our machines contain a bunch of wires with different currents running through them. So, and additionally, a wire with current running through it is susceptible to magnetic fields. We've talked about how magnetic force equals Q V perpendicular times magnetic field. If particles with charge are moving through a magnetic field, there will be a force from the field on those charges. The same thing happens if those charges just happen to be moving through a wire. We just change the formula a little bit. Hang on. What slide did we actually end on last time? I might be ahead of myself.
We did, an example with the electron moving through magnetic.
Okay, so did I actually talk about this yet at all? Okay. I'm getting my lectures crossed. I'm very sorry. Let me back up and hope I'm writing a little bit bigger on the other side. I apologize.
Wait, so that other right-hand rule is different than the one we learned, because the one we learned about was about like fingers with the velocity, and this was about current.
Correct.
But is it the same? I don't know, what's the difference? I guess I don't know.
Well,
Like, the difference between what you're looking for with the different right-hand rules.
you ultimately, both versions are still comparing direction of charge moving to orientation of magnetic field. The main problem, though, it was while your hand can represent 3 different perpendicular axes, only part of your hand can form a spiral. So we've gotten used to direction of charge, magnetic field, direction of force, but in order for this to be the spiral of the magnetic field, we have to reassign thumb to direction of charges moving. I suppose.
So the direction of the charge is the direction of the current?
Correct. I got a little bit ahead of myself. I apologize. Let's start here for right now. Let's just start right here. When you take a wire and you run electric current through it, that wire, if it wasn't magnetic before, will start acting when exposed to a magnetic field. The formula on the screen right now. Force equals current perpendicular times magnetic field times L. Is the same formula we were using previously to describe the force from a field on a charge, a single charge. And to prove that fact, I'm just going to tweak it slightly. Electric current is defined as the flow of charge over time times magnetic field times length, which is measured in meters. This is all multiplication division, so I can rearrange this however I want. So I'm just going to put Q out by itself, put the S under the M, and put V on the end. That is the other formula. Force equals charge times velocity times magnetic field. Perpendicular. So this formula that tells us the force a magnetic field will exert on a wire is the same as the previous one. This right here, where a magnetic field is exposed to a wire and the magnetic field will exert a force on that wire, this happens because the electric current in the wire is just charges moving. There are charges in there that have a velocity. So it's exactly the same thing, we just swapped the variables to more closely resemble this specific case. And this by itself wouldn't be a huge problem wires would just, if you held a bar magnet next to a wire, that might make the wire move. And interestingly, the direction of current flow would affect the direction the field will push the wire in. And right-hand rules still, the normal right-hand rules from before still apply to this. Current down, magnetic field into the board, force would point to the right, and the opposite if the current was pointing in that direction. So this is the same flat-handed right rules we've been using. This becomes a problem if you have a machine with a bunch of wires in it with current running through them, and then you put a magnet next to it. Might not always be a huge problem, but a powerful magnet next to some poorly designed or poorly secured device could cause its wires to start being dragged around to and fro and possibly being pulled out of where they're supposed to be, which is one of many reasons not to put a magnet next to your phone or your computer or your wallet. And this becomes more measurably problematic when we start talking about how a wire with current running through it produces its own magnetic field. You run current through a wire, that wire makes its own magnetic field without any other outside help. As long as current runs through a wire, there is a magnetic field being produced. And this is the field that will spiral perpendicularly out of the wire itself at a certain radius away from it. To actually determine how much magnetic field a specific wire is giving off, we have this formula. B, magnetic field itself, is equal to this constant for the permeability of free space. This is a known number. You will never have to memorize it. It will always be given to you. It is a common physics constant, though. Permeability and permittivity of free space come up pretty frequently when looking at how things move through the universe. In the case of, say, the speed of light, how fast light can move through empty space, how fast magnetic fields can move through empty space. So it's a common constant that is now beginning to show itself. But it's always 4 pi times 10 to the -7, and you'll always have this on the sheet and stuff. So this constant times the current in the wire divided by 2 pi and then the distance from the wire. So the closer you are to the wire, the stronger the field will be, and the more current you push through the wire, the stronger the field will be. So wires make their own magnetic fields. Questions so far?
Is B still the magnetic field stream?
Correct. So the strength of the field a wire makes depends on how much current is going through the wire and how close you are to the wire.
But like, how come in the other formula they were like inversely related, current and magnetic field strength, in this one? And then like here they're directly, like you said, that increase in current,
So this is the formula for what happened, the force on a wire due to an outside magnetic field. And I can label all of these. Force on a wire from when a wire makes its own field, that field won't be acting on the wire in the same way. Because, funnily enough, even though the closer you are to the wire itself, the stronger the field would be, because radius is on the bottom here. If the radius was 0, if you were in the wire itself, technically the field strength would be 0. So when a wire makes its own field, this field doesn't affect it by this formula. This is only if a field from outside of the wire comes in and is now affecting it. And ultimately, one of the reasons why an outside field can affect a wire is because it has its own magnetic field. And when those fields overlap, you get force. Excuse me. Oh. So, in general, don't put a magnet next to your devices. However, because all the wires inside your machines make their own magnetic fields that will affect every other wire inside the machine, anyone designing circuits or electronics has to keep this in mind for every single circuit board, every single component that they ever make. Because if you've got a bunch of wires inside one machine and you haven't taken this into account yet, those wires' fields will start acting on every other wire and start exerting forces between them, pushing and pulling things within them where they aren't supposed to go. To help combat this, if you've ever looked at a circuit board, or a real one, or like in a movie or something, or if you've ever looked inside of an electronic of any type, you may have noticed either etched into the board or say the wires themselves are all arranged such that they are running in the same direction where possible, and usually they're all a fixed, locked-in distance apart. If this was a circuit board, this would probably be metal etched into its surface as opposed to an actual wire stretching from one side to the other. The designers and electricians involved have to be very careful and figure out exactly where these go and where they need to stay, such that they are far enough apart to not measurably affect one another, and so that they are stuck in place so that they don't get moved around. And one way to help with that problem is by not using wires and instead having just metal pads etched into the surface of the board, because those don't go anywhere, typically speaking. So inside your machines, if you ever see like the green circuit board with the gold lines etched onto it, those are basically wires that are designed to just never move to avoid this problem. Additionally, so this is what we do to help avoid the problem. One thing we don't do is put wires across one another, because then you're going to get perpendicular overlapping fields. Because for these wires, the field will be spiraling in this plane. For this wire, the field will spiral in this plane, and that's when things get really bad. So as often as possible, lines are kept parallel to each other. If a wire has to go perpendicular, you put it somewhere else on the board with the other perpendicular lines. Designing circuit boards is terrible. I haven't even had to design a whole board. I've just had to put wire, like in my grad school work, I would build circuits and plug wires between elements on the circuit, and at most, I just had to try to keep as many of the wires parallel as I could, just putting them into the board, popping things in and out as I needed them. then electricians have to take everything there, like the board with all the physical pieces in it, make sure everything is parallel and deploy that nicely, and then shrink it and design exactly how a machine can build it. There's a ton of things they have to take into account, and I don't have the brain space for it, frankly. Having to do this every single day for every single wire is not going to be able to make it extremely, but there are people who do it. There's good money in it. So, to use both of these formulas together in conjunction rather quickly, let's say we have two wires, and some electrician didn't do the best of jobs, and even though the wires are parallel, the currents traveling through them are not. This will create a situation where, okay, if the currents point away from each other in parallel wires, then the wires will repel one another. If the currents all point in the same direction, they will attract to one another. So in this particular case, these two wires will repel. Is that what I just said?
Yeah.
Doubting all of my notes. Same direction, attract, opposites, repel. So it's kind of the reverse of how magnets usually work. Each of these wires has a different amount of current flowing through it. So each wire is going to create a magnetic field that will interact with the field of the other wire. Question is, if the radius between these wires is 10 centimeters, what is the force between the two wires?
You have to do this twice. Like the formula, because there's two eyes, or like,
Sorry, just one sec. I apologize. I'm going to write down the other formula real quick. Okay. I'm adding in one extra line. I apologize. I needed to specify one more variable for the formulas. Can you repeat the original question? I'm sorry.
that because there's two cards, would you have to do it twice?
Well, it's a good question. I'm going to do it from the perspective of one wire and show how that work would actually be the same if we started from the other wire. So for both wires, they're both this far apart. We know their currents, and we're going to look at a 1 meter stretch of that wire. for each one. We're looking at the force involved between 1 meter of each wire. So, let's say from the perspective of wire 1, wire 1 is the 20. 20 wire amp is on top. So let's say the force on the 20 amp wire is going to be equal to the current in the 20 amp wire times the magnetic field acting on that wire, which is actually the field made by the 10 amp wire, because the 20 amp wire's field won't affect itself. In this situation, 20 amp wire will only be affected by the 10 amp wire's field. And then L would be 1 meter for both. So we want to know force. We know the 20 amp wire's current, 20 amps. So we need to figure out the magnetic field from the 10 amp wire at the 20 amp wire's location. So, the second formula for magnetic field of the 10 amp wire is equal to U naught permittivity times the current in the 10 amp wire divided by 2 pi r. So this is just variables from the 10 amp wire. Plug everything in to find this number.
Why is the radius the same as the length?
It's not.
Oh, wait, I did, sorry.
They could be. It could be, these wires could be a meter long, they could also be a meter apart. But in this particular case, we just got 1 meter long and 10 centimeters apart. You guys agree with 2 times 10 to the negative fifth? Okay. And remind me, what is the unit for magnetic field?
Oh, Tesla?
Correct. So, we now know the magnetic field that the 10 amp wire is making at the 20 amp wire's location. Before we plug that number in, however, I want to show you something. I'm going to take this formula and substitute it into here to show what they would look like completely combined. So substituting this in for B, that would leave us with force is equal to current 1 times permeability constant times current 2 times length divided by 2 pi r. All mixed together like this, it actually doesn't matter which wire's perspective we're looking at, because theoretically we could just swap where we wrote these two numbers and it would be the same as if we'd started from the 10 amp wire and was finding the mag field of the 20 amp wire.
Wait, would the radius ever be, the radius is the distance between them.
Correct.
So the radius would always be the same.
Mhm.
But the only thing that would change would maybe be the length, or is the length always gonna be the same?
For this question, I've worded it in such a way that we're comparing 1 meter of each line. One 1 meter of each cable is just hovering over the other. Things would get weird if the wire lengths were different, but that would be weird to the point where it wouldn't be worth solving at this level of algebra. So I would never ask you that. So by combining the two, it ultimately would not matter which wire's perspective we're looking at, because Newton's third law tells us the force that one exerts on the other will exert back. And this math just verifies that. The algebraic jumble wouldn't matter which way we started from. Any questions about that? It's okay if you don't know what your questions are yet. You can ask them later. I know that I've been making a lot of phone calls recently because of taxes and planning a wedding. And everyone always asks me, do you have any questions? And inevitably, I can never think of them when I'm asked that. I always tell them, I'm going to think of them in 30 minutes and I'll call you back. And that logic still holds for my math, for my classes. Please send me your questions when you think of them. Because, I would never remember to ask them in the moment. So, we went ahead and found the 10 amps magnetic field at the 20 amps spot. It is worth noting that the two wires would be making different amounts of field. Like the 20 amp wires, if we were looking at the 10 amp wire's location, the 20 amp wire would be making about twice as much field at this spot. But the ultimate force would still be the same, because the force depends on the current in the wire the field is acting on as well.
Wait, can you repeat that?
Yes, I can. At the 20 amp wire's location, the 10 amp wire is creating this much field. And it's acting on the current in the 20 amp wire. If we were to reverse our perspective and look at the location of the 10 amp wire, the 20 amp wire has twice as much current in it. So it would be making twice as much magnetic field. However, that doesn't double the force, because the current in this wire, the wire being acted upon, is half. So twice as much field acting on half as much current comes out to the same force.
Like we would have put in 10 instead of 20 for the bottom right there.
Correct.
Yeah.
Like we would have put the 20 in finding the magnetic field, but then this would be 10 instead.
Okay.
So it comes out the same either direction.
But they do have different magnetic field strength.
Correct. Different field strengths, but acting on different currents. That would ultimately cancel out. And this should ultimately give us 40 times 10 to the negative fifth, which should be 4 times 10 to the negative fourth. Very good. And that would be a force. It is in newtons. And if you were asked for direction, since the currents are in opposite directions, it would be repelling. So both of these wires would be being pushed away from each other.
Wait, so the direction is
Outward. Direction is outward. Kind of like with the E field, the electric forces we were looking at a couple of weeks ago. The formula only told you repel or attract. Same here. Okay.
Wait,
Yes.
if they were going in the same direction, we know that they attract,
Yes.
but how does this affect the math? The math isn't affected, right? Isn't
The
it
math would not be affected,
just the direction?
just the direction.
Okay.
And instead of sort of harkening back to the electric force calculations, if you were to look at the force between two protons, you would get a number for your answer and they would repel. If you switched one of them to an electron, the number's the same, but the sign would be opposite, which tells you attract. So, same numbers, same absolute value, just different assigned direction. Okay. I want to at least show what we're going to look at tomorrow. We start looking at it because it's just the next step from this. The math we just did was for straight wires, just straight lines.
Like in the thing, boards or board thing?
Right. However, if you remember the inductors we used in lab last week, those are big coils. So you can run current through a loop. Literally, the wire is just in a loop shape. And ultimately, the same thing will happen. The wire, the wire with current in it will make a magnetic field, and the wire with current in it will be acted on by other magnetic fields. That is all still true. That said, if the shape you're looking at is a closed shape of wire,
Wait, what does that mean?
what it means is if you were to put a coil or a closed loop of wire in a magnetic field, rather than just being pushed to one direction, it would start spinning. Because, and I'm going to reduce this to a square for simplicity's sake. So let's say that the two sides of this square loop are hooked into a circuit, so current is able to flow into the loop and then back out the other side. And let's say there is a magnetic field in this region of space, and that magnetic field I'm confusing myself once again. Okay. So the way that I've drawn it, let's say that the magnetic field in question points down. So, magnetic field points down, and this is a closed loop with current running through it. By virtue of the fact it is a loop, even though the current is always going to flow forwards, It's always going to go straight through from one side to the other. From a perspective outside of the loop, the current is going to point in different directions at different parts of the shape. So just looking at the top of this square, magnetic field down, current pointing to the right, what direction is the force going to be?
What is your charge? Wait,
Oh, the current flowing is the charge.
Okay.
So charges are in the wire, they are moving to the right. So velocity of charge points that way. Let's say the breakdown rules.
Like negative Z?
Charge, wait, you're talking about the force?
Yeah.
Okay, yes. So field down, velocity that way. The force would be in the negative Z axis right here.
Wait.
Sorry, I'll just write negative Z. But then, down here, the direction is just arbitrarily pointing the other way. So what would the force direction be down here? Positive Z. So on either part of the loop, only looking at top or bottom, ignoring the sides for a second, the forces would be in opposite directions. So at top, the loop would be pushed that way. At the bottom, the loop will be pushed this way. And when you push in two different sides of one shape, what's going to happen to it? It could, if someone was just gripping the ends of the wire in place, then the forces would just keep pulling and keep pulling as far as the wire would bend. But if instead of holding this still, if instead this was allowed to spin about an axis,
Oh, then
it would just constantly be causing this loop to spin.
Wait.
Top gets pushed that way, bottom gets pushed that way.
Spin like this.
It's just going to spin counterclockwise.
Counterclockwise.
From where I'm standing,
Oh.
counterclockwise. From where you're sitting, yes, clockwise.
So, there is no force, like, on the right side of the circuit?
There would be, but,
Because they're not perpendicular, so I don't know.
oh, yes, that's a good point. Here, the current in the field would be parallel, so there wouldn't be any force. Thank you.
So like, the force disappears and then it comes back, or like, or,
No.
yeah?
Yeah.
Oh.
It's only being exerted on a part of the system. Like, the magnetic field would only be pushing on this piece of wire and this piece of wire. Now, usually, sometimes we make them squares, sometimes we make them circular loops. And even though the math gets a little funkier there, it's still the same thing. A circular loop would still start spinning. And this principle forms the foundation of all electric motors. Sometimes the motor might use the reverse principle, where instead of putting a wire with current inside of a magnetic field, you put a magnet inside of a loop with rotating current in it. But either way you slice it, this creates spinning motion. So any electric motor that creates spinning is caused by this or the inverse. It is caused by this. So all electric car wheels spin because of this. The vibrate function on your phone spins because of this. Basically, any electric movement, if movement is powered by electricity, that's going on somewhere inside of the machine. Because that is turning the electrical energy into physical, mechanical, rotational energy. And gears and gyros are able to take that energy and turn it into whatever the machine needs. So we will pick up there looking at the applications and meanings of this tomorrow. Any questions? You're set up in the morning. Okay. You'll be working on your assignment. Know what issues you have as you're working it, and have a wonderful day.